Carla.
The closed path is when the start meets the end. So very nice representation is over here. Closed, not closed. This will be important because we will be talking about these things quite a lot. New important fact. If and only if, we kind of had it before, IFF. If and only if means goes both directions. This integral, line integral over C, is independent of paths, if and only if. It gives you 0 for every closed C. Kind of makes sense because when you are biking on the trail and it's a closed circle, right? And there's a wind, say, towards your face. It was towards your face right now, but then when you turn, it became perpendicular. And then when you turn, it became helping you. And then when you turn, it's still the same direction. In total, it gives you 0. Because remember, line integral, one of the ideas is to accumulate all the arrows of the vector field on the way. If it's positive, it means wind was helping you. If it's negative, it was into your face. If it's 0, wind did not do any help or damage to your biking. So if you'd go in circle and complete one circle, it accumulated both negative and positive for the same amount. Thus, no matter which path you choose, it will still give you 0 if C is closed. This will help you in your homework and exam. We can put examples like this. No need to integrate anything. You just say, oh, it's 0 because it's closed. We will have this example today if we have time. Then you don't have to check anything. But then, this is important. It's independent of paths, if and only if. Again, F is conservative. If and only if. F is conservative. And that is important. Apparently, F is conservative. Remember, when we found the F, small f, that was differentiated and gave you the vector field, then you can choose any path to calculate the vector field. So, it's very interesting that this is why conservative fields are so important, because then I don't care what kind of path I'm building. Path will be just a tool, kind of slowly answering your question. I'm going from here to here. Either I'm going like this or I'm going like this. Doesn't matter. The path will be just intermediate tool to calculate the integral, and the integral will give the same result. So you don't have to write this down. C is closed. Sometimes this integral called the circulation of F around C and measures how many times F loops around C. For conservative F, it gives you 0, so it's called irrotational. Do not rotate. I never heard about this, so it means it's not internationally known, but it's cool information. This is important. We just wrote this down, but maybe you want to summarize. Conservative vector fields are nice because it's easy to calculate by the fundamental theorem of calculus. It's independent of the path. You can choose this path or this path. C1, let's do this. Any path is fine from A to B. And it's irrotational, so it doesn't rotate. Remember, if it rotates, it gives you 0, so we don't do that one. Conservative field. Now, okay, how to figure out that vector field is conservative? We just told you that, you should figure out this F. If you could integrate, then it exists, but that's too complicated. Integration in general is a complicated process, so let's figure out some kind of ways to check. There's a very handy trick we do for 2 dimensions, and the upper dimensions we're going to do in 13.5. Very nice trick is, I wanted to write this down for you. I remember why I skipped the space. Very nice trick is this one. Let me help you to write it down. Nice. Suppose, so it's only in 2 dimensions. Let's see, 2D. I use let instead of suppose. F is a gradient field. So delta, it's not delta, it's del F, partial derivatives, gives you a vector field. Then let's call partial derivative with respect to x and partial derivative with respect to y only 2 dimensions. Let's name them somehow nice, and usually it's P and Q. That is international notation. P and Q, we even use it in Russian as well. P and Q. So we're gonna call Bless you. That's actually good enough. So we're going to call P partial derivative with respect to x and Q partial derivative with respect to y. That's just notation. So let's say let's call them. To check if the field is conservative, you need to do this interesting trick. Instead, integrate other way around. No, differentiate. Differentiate the other way around. Differentiate P with respect to y and Q with respect to x. And see if they match. Now, this comes from this idea we had before, that f with respect to x and y matched as f with respect to y with respect to x. Comes with the same idea which called Clairaut-Schwarz theorem. Kind of this is where it came from. If that happens, the field is conservative. And that's what we're going to be using, and that's going to go to the third exam. Check if field is conservative. It's actually very simple to do it, but you need to remember what to do. You take the first component and differentiate it with respect to y. You take the second component and differentiate it with respect to x and see if they are the same. Visually, it looks like so. If conservative fields don't have any loops and gaps, it's not supposed to be a donut and it's not supposed to have gaps. So if it's a donut, that is not good. It's not conservative. If it's, what kind of food is that?
Burger.
I'm actually thinking about
Cheeseburger. Buns.
Americans, cheeseburgers and buns. I'm actually thinking about
I wish I had a sandwich.
the French cookie. What's the name of it? Macarons. I'm thinking about macarons. Yes, because they're tasty. Macarons, yeah. So intuitively, I actually did not know that conservative is translated as does not rotate. Not conservative is a rotational one. So we want to work with wind that doesn't have any loops. And that is why it's so hard to predict or work with tornadoes or current in the ocean that becomes whirlpools. Yes, thank you. Because they are not conservative, so it's hard to work with them or predict what they do. Well, they are predictable, but it's hard to figure out the speed and so on. But if it's a wind going one direction, another direction, surprisingly, it's more predictable, it's easier to find derivatives and so on, and integrate. Let's do the example, finally. Let's do this example. Calculate the given integral. Let me zoom in for you. Calculate the given integral, which is here, found it. Which is sine y, x cosine y minus sine y, and c is line from 2, 0 and 1 pi. Okay, let's do that. And this is basically one of the most important parts of this class, to be honest. So, solutions. You can sketch the graph. Jacob is keep complaining he doesn't like sketching the graphs. So to be honest, for these questions you don't have to. That's a good part of it. That the whole idea of the line integral, you can avoid graphing or parameterizing everything if it's conservative. So I would do the very first step to figure out if it's conservative or not. Yes?
Yeah, can we just look at conservatives like fancy talk or like differentiable, but for a vector field?
Conservative, yeah, I would say it's exactly what you just said. Conservative means we can differentiate and integrate. Yeah, so remember in calculus 1 we say, oh, some functions cannot be integrated and stuff. Conservative's nice, smooth, integratable, differentiable. Yeah. Okay. Yeah, very good intuition. Yes?
Is a vector field that's radially out from a center point conservative?
Usually, yeah. So it's not rotating, so it's fine. Good question. But we had this example at the very beginning, I think, was vector fields. I will not go back. Yeah, and it was conservative. But from now on, we'll have to check. And the 2D check will be simple. In 2D, we're going to check using this formula, but in 3D, it will be more hard. So we're going to go to 3D soon. Is it conservative or not? Yeah. To figure out if it's conservative or not, I will have to figure out what is my P, what is my Q, and then differentiate it with respect to the other variable. What is my P? Sine of y. So take a pencil maybe for the first time and name this. This is your P and this is your Q. That's a little bit too much writing, so to be honest, I would just start differentiating it right away. P, we're differentiating with respect to second variable, y. With respect to second variable. That's the whole idea here. P will be differentiated with respect to second variable, while Q is respect to the first one. To make this kind of flip of the order. Derivative with respect to x and y, and derivative with respect to y and x. Because P represents x component. That's why it's easy to memorize. Derivative of sine y with respect to y is, good job. What is going to be derivative of this second component but with respect to the first variable? X cosine y minus sine y. So it's not a product rule, be careful here. With respect to x, cosine y, yes or no?
No, negative sine y.
Imagine x is only important part here. So x is over here, everything else is a constant. Derivative of x is 1, constant cosine y survives, minus sine y is 0. Make sense? They should match, did they?
Yeah.
Matched, yay. Since P with respect to y matched with Q with respect to x, so I will do fine, since, then the field, let me say, just the field F, is conservative. Unfortunately, such an easy trick only works for 2D, but it is fast and nice. So this with just one step, and you check it, and you show it on the test. If it's a written part, done. Very good idea. Since it's conservative, step 2, yes.
Is there a sign for conservative?
No, not really. I don't remember it in Russian either. Just a word, yeah. And again, in Russian we call it potential. Very interesting. I guess they make more connection with physics there. So then we will have to find antiderivative. And this is a new topic. I will put it in a different color for you. Okay, since it's conservative, I will do like this. It's conservative, and I will keep going. And it means we can find f such that, now we can find small f such that when you take partial derivatives of f and create the gradient, it will give you this capital F, which is given as sine y, x cosine y minus sine y. So we need to integrate, and we did not teach you yet how to do it. So this is, I wanted to put it in one example. Step 2, how to find antiderivative. I'll put it in the blue color. Find antiderivative. Last class, I remember we did it into antiderivative. Yes. Last class we did it intuitively. Sagar was helping me, I remember. It was x times y kind of thing, remember? Derivative of one gave you that, derivative of another one gave you that. Now we're not going to do it intuitively anymore. We will have a process going on. Yes?
Is it always going to be p, y, 2x?
Yeah, these ones are always the same. This is the theorem called here. The theorem, bless you, that was a very cute sneeze. How to find it, the field is conservative. Differentiate first component with respect to second, y. Differentiate the second component with respect to the first, x. Okay, so let's do it. This is important. This is a very good written question on a test, because finding antiderivative is fun. You usually know how to do it. It's amazing. I'll put it in blue color. So let's write down again f, which is given, but we're looking for the small f, which gave me this field. This equal sign came from checking it is conservative. Thus, I can write down left-hand side is the vector sine y, comma, x cosine y minus sine y. That was given. What we are looking for are these two components, f with respect to x and f with respect to y. These are not given. We are looking for them. Vector properties, lecture 1 of this class, we told you that each component should be equal to each other. So we can now write down that f of x, f with respect to x, right away is sine y. Boom. F with respect to y, right away is x cosine y minus sine y. So we got this part. From here, we need to figure out f. So what are the integral of each part with respect to corresponding variable? Let's do it. And that's why it's not guessing anymore. So I will call it this number 1 and this number 2. Number 1, let's integrate the number 1 equation with respect to x. Be careful with that. Integral, I will do like this. F of x comma y, so 2 variables here, equals integral of sine y with respect to x. So it's dx. That is important here. What is the answer for this integral? X sine y, anything else? Plus c.
Oh.
Ha! Minus 5 points, yeah? Anyway, plus c. That is one of the guesses what this function can be. But we need to use the other equation, number 2, to see what is happening from there. Because there are infinitely many answers for this integral. There can be something more there. I can always add plus cosine y, that's a constant, minus ln y, that's a constant. Anything with y is a constant. So since it's so many infinitely possibilities, equation number 2 would tell us what is happening with respect to y. With respect to y, this function will be integral of x cosine y minus sine y with respect to y. So dy, that is very important because second equation is derivative with respect to y. So we are undoing differentiation with respect to y. Equals, what is the answer here?
Negative x sine y.
Let's see. X sine y, check in your mind, derivative of sine y is cosine y times x.
Cosine.
Plus cosine y, agree or not?
Plus c.
Plus some kind of c, can be different c, you can call it the same. It's kind of not the same one, maybe called k, I don't know, anything is fine. In this note it says junk, because it's not important. That's true, it's not important, some kind of other constant.
Isn't that a negative? Negative?
Let's check. Derivative of cosine y is minus, sine matches. Derivative of x sine y will be x cosine y matches. I kind of agree. How about you guys?
No, it's a
Plus some kind of stuff. Now what we do here is we're going to collect this information from number 1 and number 2 into one function. Thus, f of x and y equals, without repeating the same pieces twice. The same pieces x sine y and x sine y. You don't have to double it. You copy it once. X sine y piece is there, but the second equation gave you a new piece, which is cosine y, plus a constant which we don't care about. Why we don't care about? Because any will work. Any example of this function will work. There are infinitely many possibilities, but since any works, let's assume that the constant is 0. So this is the function f, which when we differentiate will give you the vector field we had. Let's check that in a second. Let me tell you just a second. We collect all the terms without putting things twice, so we don't double count it. Let me write down. Don't double count terms. Well, I mean repeated terms, right? So anything new should be counted. And then there are other possibilities, so let me do like this. Note. One note, don't double count it. Note number 2 is there might be other antiderivatives. Let's do possibilities. Such a long word. Possibilities. TTTs. Possibility. No. See. Possibilities. I need just to copy it from the screen. Still don't do it right. But we just need one. We just need one. And since 1 is needed, we assume c is 0 and there's no other constants there. Because again, there might be other constants and stuff. We can check that this is the answer, but there was a question there. What do you want to ask?
What? Oh, never mind.
Okay. Any questions, concerns, or comments? I was just teaching about this Questions, concerns, any critics? Graduate students were very surprised. Like, you should be very open to critics. So we can always check if you want. That's what we do in my Calculus 1 class. Oh my gosh, you can check integration. Look at that. Yeah, we just perform integration. You know how to check it. I want to differentiate. I want to find gradient of f, right? Gradient of f will be derivative of this function in the box with respect to x first. With respect to x, it will be sine y plus 0. And then with respect to y, it will be x cosine y minus sine y. Does it match? I'm going to the very original one. Ta-da! Matches. So you did not mess up. You, me, we did not mess up. Very good. Make sense? So you can always check yourself on a test. That's very convenient. Now, why did we do that? The moment you found the antiderivative, no need to parameterize anything. No pictures in it. I never even draw the picture for you of this path from 2, 0, 1 pi. So convenient. No need to draw the cylinder, the parametric stuff, the first quadrant of anything. If you can find antiderivative, none of this is important anymore. Polar equations, spherical equations, no. You just know the formula. Step number 3. No. Step number 2, 3, yeah. Finally, you build the line integral. Line integral over C. Without explaining what C is. Because the theorem just said, if field is conservative, we don't care what path we're using. So we don't never have to parameterize it or describe the C. Line integral of f dr over C is going to be, by the formula, it is this gradient dr, that was the original formula, dr, and then the fundamental theorem of calculus for line integrals told us, well, actually, if you found the integral, you just plug the top minus the bottom, but in 3D, it's the end minus the start. End minus start. So you just need to remember start. You just need to go and check what start. The points where. That's all. The end point was what? 1 and pi, they gave it to us. And the beginning was 2 and 0. Where do we plug this? Into the thing we just found. Into the box, exactly. So, it's going to be, now you know how to plug both variables, right? X and y, maybe put a note. This is x, this is y. Plug the first one first. 1 sine of pi plus cosine of pi minus, plug the second one. This is x, this is y. Open parentheses, don't forget. X is 2 now. 2 sine of 0 minus cosine of 0. All this end up to be minus 1 minus 1, which is minus 2. Minus 1 and minus 1, which is minus 2. Boom, done. And that's why line integrals are so popular. They're used in physics, engineering, math, of course, lots of stuff. Because describing something is usually challenging, but if you can find antiderivative, that's actually hard work to find antiderivative, but if you can, lots of possibilities are open for you if you know that the field is conservative. That's why it's so crucial. Questions? What do you think about that? This is a very nice example of problems. You just need to know the theory. But to be honest, the whole work is doable, right? Like when I show it to you, I can feel you guys agreeing on this. You just need to practice not to forget what to do. Because I do understand we teach you the very last months lots of formulas. Lots of new complicated methods. If you can be calm enough to distinguish them, you can do each. Just kind of too many, I would say, in the last months. Yes?
So in getting a negative answer for the integral, what would that mean?
Yeah, that's a very good question. Has anyone tried to guess?
It's not volume.
Yeah, but that's not volume. So who remembers what line integral represents at some point?
The shadow, 3D.
Shadow in 3D. Oh, well, that was a good explanation. But why it's negative then?
Is it like under the plane?
That's a good one. Oh, there was a good animation about that. Under the plane is a good one. More? Yes? This one will show you right now, actually, how it goes under the plane. See? Above the graph and then below. But what does it mean to be below?
Oh, it's the It's against the.
Against the wind or against the force. Yeah, so I wanted you guys to kind of remember that. The main explanations of this, the two good ones I like is those two. First one, it's wind into your face and it was very hard to bike, but at some point it was helping you. But the total negative means it was against you more than helping you or not disturbing you at all. Or in this case, as you can see, the negative will show up over here when the wind is into your face. So let's see that. The negative will show up over this place. See? Boom, negative. And it stays negative almost until the end, and only the end finally starts helping you again. So if the negative is more popular than positive, the final answer will be negative. Good question, thank you. You kind of helped me to review that moment. So let's see. More questions, ideas, concerns? Yes?
Doesn't the second part of that, like, wouldn't be -1 + 1?
Let's see. Sine of 0 is 0. Cosine of 0 is 1. Minus minus gives you plus. Did anyone actually check?
No, it's supposed. It's the answer is correct. It's just supposed to be 2 sine of 0 plus cosine 0.
Yeah.
When you
Yeah, this one is plus. You're right. Fix this to plus. Yeah, and then it becomes minus. Okay, good job. Yeah, good catch.
Wait, which one goes to -1 for the first?
Sine of pi is 0, so only this one. This one is -1. Cosine of 0 is 1. Cosine of pi is -1. Now, how about this example? Put it on. This is what you're doing right now, or you finished doing with your homework, right? With all, well, my other class is still doing homework on polar spherical equations, and they hate it. But now this is the idea. So you have this vector field. Again, vector field is your computer, your machine, your device describes some kind of magnetic field happening outside of your house, and you're like, wow, what is happening here? Should I even go out? What if it's gonna crash me, right? So the machine gave you, the magnetic field outside of your house is described with these equations. And that means you want to walk from home to school. So your C is your path, how you'll be walking. You decide to take a walk around and go back home just in case and because you forgot your phone. So it will be a circle centered at 0, 0 of radius 2. So you decide to have a circle and walk around. Will this field help you to walk around? The new magnetic field show up. Maybe there's like a black hole show up on campus. Will help you maybe speed your walking to campus, right? It will drag you there. You take a class and then you go back. So what is happening here? That's kind of the funny explanation I can explain here. No picture needed. Oh, it actually says counterclockwise. Fine. So there's lots of information. Doesn't always mean that you need to use it. Guys, figure out some kind of English notation for this. Counterclockwise. Every time so much writing. Oh, there is?
Yeah.
Did you say CW?
CCW. Clockwise is CW.
Oh my gosh, you guys just opened my mind into new possibilities. It's like people told me the resurrective final term. I never heard it in 9 years.
I don't think I've heard CCW
Right?
before.
No, I never heard this one either. Interesting. Do you all know what resurrective final is?
Yeah.
See, I did not know. I mean, I knew the idea, but I never heard the term. So we do have a resurrective final in this class. I decided to make it for you to know, to help your grade if read it. So let's check if it's conservative. Then we don't have to do any extra work. We have 5 minutes, so let's do that. Step 1, is it conservative or not? So what is my P? P will be differentiated with respect to second variable y, but P is 2y. Derivative of 2y with respect to y is 2. Okay, that's very convenient. What is my q? Q is 3x, but we will be differentiating with respect to the first variable, x. There is 3. Did they match? No, they did not match. So let me tell you, there's a funny thing here. Connecting the two. Oh, this one. So, if they did not match, that means it's not conservative. If it's not conservative, we're not allowed to use this formula. Ton, ton, ton. So it's not that easy anymore. And that is the bad part over here. And then what should we do? Then what we're gonna do what we taught you before. In that particular case, you will have to create parameterization and then describe the circle with all this kind of stuff, which means step 2. Then we do the whole process parameterization. So not conservative. Cannot use the convenient formula. Cannot find. There's no such an integral. That's the idea. There's no such a function that will be differentiated and give you 2 and 3. So and give you those 2 functions, 2y and 3x. Thus, we will have to do parameterization and all that kind of process. It is, and we know how to do all this. You draw the picture. That's what some of you don't like. You have a circle. It's counterclockwise. The circle is radius 2. It says that. Then you build it as x equals 2 cosine t, y equals 2 sine t. You have to figure out what your t is. T is completing the full circle from 0 to 2 pi. So whatever we taught you before, that is a backup plan now. It's actually, not that, it's important, but we hope to avoid it. And then you build the integral how you always do it. The line integral of f dr is integral from 0 to 2 pi. Your function now is, in terms of new functions, 2 cosine t and sine t. What was the function name? Here it is. So now it's going to be y is 2 sine t and x is 2 cosine t. Let's write it down.
3.
3. Yeah, thank you. No. Radius is 2.
Oh, yeah.
Radius is 2. So it's like so. And then we will have 2 sine t, but multiplied by 2, comma. And then 2 cosine t, but multiplied by 3. That's a vector. Multiplied by, do you remember what?
The derivative of the parameterized equation.
The derivative of the parameterized r with respect to t. So we're going to have the first component is derivative of 2 cosine t. So that comes from here, which is minus 2 sine t, comma, 2 cosine t. And the answer should be a number because it says dot product, which is called scalar product. This takes us to the previous chapters. You will end up to have integral with respect to t from 0 to 2 pi minus 8 sine squared t plus 12 cosine squared t dt, and it gives you 4 pi. So it's positive. That means from going through that path, the magnetic field of the black hole on campus actually helps you by dragging you there, but only if you go counterclockwise and so on. So now path is important here. So a question for you, but didn't I just say when the path is closed, the integral should be 0? Remember I said that when you go in the circles, we don't even have to calculate it anymore because you kind of the whole thing just add up together. What did you say? Yeah? Anyone remembers? Note. Just a second, let me finish. Even though, oops, that's not how you write. Even though C is closed. In the previous notes, I mentioned to you this.
Oh, isn't that one for conservative?
Yeah, that's why conservatives are so good. I said that, let's see. If the integral is 0, that works for closed C, for every closed C, but it should be conservative. And that's why conservative passes are so important. We just checked it's not conservative. That means something is going on here. Maybe a whirlpool. So maybe the gravitational force is not just going in a circle. It drags you in somewhere. And that is why it's not equally canceling it out anymore. So even though C is closed, comma, integral f dr is not 0 because that's another argument that f is not conservative. It's not a nicely looking field. Conservative. So there are lots of kind of mathematical terms, mathematical effects that people know they are hard to work with. For example, singularities are hard to work with. The discontinuities we know hard to work with. Some kind of asymptotes are hard to work with. Not conservative vector fields are hard to work with. And now you know why. It's hard to integrate, differentiate, and so on. Wait, just a second, there are 2 questions. There was here one, and then there was, yeah, you go.
What would the bound be if you went clockwise?
You will just probably put one of the negative, and then the bounds will be the same. The moment you put negative, it kind of turns the direction. That's a good question, yeah. Yes? Oh, that's good. Good job, people.